Starting stream, starting recording, and we're off to the races. Okay, sweet. Well, welcome back. Good morning, afternoon, evening, depending on where you are in the world. It's Avi, Matt, and it's the zkEVMs. We had our first one on zkVMs, zkTLS, and the intention with the zkEVMs is both non-cryptographers and how do you bridge the gap essentially between academia and the research that goes on with zk, and now applying it to the impact that you see at as an end user with the products that you might interact with. And this today we'll talk about, I guess, zkRollups, and kind of like generally rollups, and then zkEVM, and brief mention of data availability as well and how that fits together. But
yeah, that's interesting. We did talk about zkVMs last time, but we didn't mention rollups even once. Although rollups are like kind of projects which have a product market fit right now, because they are being deployed in production. Right, the scroll is in production. I think it's on mainnet. I'm not sure. zkSync probably recently have gone on mainnet. So yeah, rollups are working, and they're scaling Ethereum. So which obviously makes them like pretty interesting use case of zk, or rather we should say validity proofs, because rollups typically only use succinctness and don't really use the zero knowledge aspects of the zero knowledge proofs. But yeah, I think like maybe we can describe like the rationale for a rollup, like why do you even need a rollup? I think Vitalik had this blog post, or maybe it's like a Ethereum Magician's post, I think in 2020 or sometime around that, which kind of presents a rollup-centric roadmap for Ethereum. And it was not clear, like in 2020, that like how Ethereum will scale. There were a lot of different paths that people were pursuing. Sharding was the big one, the full sharding, not the dank sharding of today. That was being worked upon for a long time, probably since 2016 or something. And yeah, in 2020, I think there was a lot of clarity in Ethereum ecosystem that like we should really pursue the rollup path. And what's interesting about this is that you kind of get you kind of like balance the scalability trilemma. For the people who haven't heard of scalability trilemma, it's like a triangle which has like on three of its sides you have decentralization, security, and scalability, and you can only pick two essentially. And most of the chains, like Bitcoin, they forego scalability in the favor of other two. Similar with Ethereum, but with Ethereum and with the rollup-centric roadmap, you can get scalability too with decentralization and security by just moving all the execution away from L1 and to L2s. And rollups are like one type of L2, which can inherit the security of L1. And yeah, and there are like two types of rollups that were proposed at that time. One was optimistic rollup, which now is being deployed by Arbitrum and Optimism and Base and all these and other such projects. And the other one was zk rollup, which is a misnomer because it should be really succinct or validity rollup, but like now we are we have to stick with zk, even though it's not zk. But yeah, the zk rollup, um, which would use validity proofs, the proof of execution, um, to uh, to basically ensure that the computation that happens on L2 is actually a valid computation. And the crux of a rollup architecture is that, like, if you do a computation on L1, any kind of transaction that you send on the network, it has to be executed by all the nodes on the network. So if you have 6,000 validators, like the 6,000, one computation will be executed 6,000 times, and it just sounds inefficient. Like, why? Like, why would you want to do the same thing like 6,000 times? And the answer is you want to do it because that's the only way to find out that, like, none of the 6,000 validators have cheated, since everybody executed the same thing and arrived at the same conclusion. Um, yeah, but like, if you can magically, like, reduce the number of times you have to execute the same computation, maybe you can have like this one particular node, call it sequencer, and the sequencer's job is to execute the transaction and make a proof that, like, this execution is correct. Then, like, the same transaction doesn't need to be executed 6,000 times in 6,000 other nodes. It just one the sequencer will just execute it, and others just verify and update their state, and the blockchain will move on. So that's kind of like a basic overview of why rollups are important. Um, and and yeah, maybe next we can go into a little bit into how the sequencer works and how it is actually secure. How do we know that's not cheating? Um, yeah, what do
Yeah,
you think?
yeah. I like the maybe run back or summarize some of those pieces. That was a great introduction of like rollups built up of, there's other things outside of just even rollups. There's, L2s, and this is one particular design. Uh, Essentially reducing the amount of computation that you want to do, as well as bringing it away from layer one, like using Ethereum with the EVM is pretty costly to execute all these transactions, right? So if you can do it on another chain and then have a way to verify and ensure that those are valid transactions and essentially state changes, then you reduce the cost. You can potentially also increase then the throughput. So there's some big benefits that happen when you aren't working at the basement level of this house that is secure computation, building on top with rollups or L2s here. And I guess there's maybe before going into the sequencer and side of things, you mentioned I guess a couple of pieces. One, this magic. What's kind of going on with this magic of how are we, like, what's happening essentially as these transactions, um, how are we able to like ensure that this is valid, not necessarily going, uh, don't have to do a deep dive into the zk itself, but rather maybe like what's the process of like what happens when a transaction is like submitted and then goes through, and maybe that brings it into the sequencer side of things as well.
Yeah, yeah. So the sequencer is like one node in the rollup chain, or a rollup network, which is responsible for executing all the transactions. And generally, at this point, at least, most of the sequencers are run by the foundations or the team that's building the rollup. With and lot of them have a plan to decentralize the sequencer, which is, I don't know what's the progress there. And uh, but the thing is that, like, eventually you don't want like one central party company or organization to be in control of the sequencer all the time. Just for the sake of decentralization, it should be permissionless. Like, anybody who is willing to put up a bond, a stake, or something like that, and if they do something malicious with that, they could be slashed. So yeah, so I think the goal with decentralized sequencing is that like eventually everybody who is willing to create a sequencer should be able to create a sequencer. But like just to describe how the sequencer works is that like it's just like uh, a special node in the network which can sequence the transactions. So that's where the name comes from, sequencer, because its whole job is just to create like listen for transaction and sequence it in a certain order. And this also leads to MEV, which we probably wouldn't talk about in this segment, but like maybe sometime later. Um, but yeah, so if you're there are like essentially three kinds of transactions that the sequencer could get as a rollup. Um, so one is like when a user is trying to deposit their mainnet Ethereum into the rollup, and that's kind of a deposit type of transaction. And it's essentially cross chain transaction because it is crossing the L1 and going into L2. And similarly, there's a withdraw transaction, which is also a cross chain transaction. But apart from these two, the third type of transaction is like uh, it actually stays within the rollup within the rollup chain, and it doesn't has to go to the L1. And that's where like all the scalability comes from, right? You don't have to put all these other all the L2 transactions to L1. You do have to put the transaction payload to L1 because that's really important for the security that the rollup provides, because otherwise rollups can execute a data withholding attack by not presenting some transactions to the L1. So all the three type of transactions that I mentioned, they are all their payloads are being put on L1. Earlier, call data was used for these type of transactions, but recently, like with the IP 4844, the big rollups like Base and Optimism and others have switched to using blob space, uh, which should benefit them because it would be cheaper than just using call data. At least it's cheaper now. You'll see. Uh, yeah, yeah, and yeah. So essentially, like just to summarize what the sequencer is doing, it's like listening for transactions. It is uploading all the transaction payloads into L1, so that could be retrieved by anyone at any time, and it is executing that transaction locally and putting those like the output of that execution. We can think of them as like state roots, and so it is submitting the transactions, raw transaction. It is submitting the state roots. The problem is like how would you prevent the sequencer to create like an invalid state root, because like that's something that could do. Um, it could just decide to not run the execution correctly and just produce a random state root and put it there. And but somebody has to like check that that this sequencer is actually producing the right state root, and that's kind of the magic that we referred to earlier. And it could be done in one of the two ways. Like the simpler one is like how optimistic rollups do it. What they do is like they create this challenge period that whenever a sequencer posts a state root on L1, it could be challenged within like 7 days or 14 days. I don't know which. Some rollups have different configurations. And if nobody challenges that state root within that challenge period of time, you can consider it as final. And that's how this optimistic proofs or fault proofs or fraud proofs work. Uh, and the problem with this is like the challenge period is not very user friendly, because it creates this barrier, like user have to really wait so 7 days to know that their transaction was final. It breaks the composability, and that's where like those problems could be solved by validity proofs, because validity proofs are they are actually truly magic because they use the zk uh, or sussing
zk's
nets at
magic, yeah.
least. Yeah. uh, and how, like in a nutshell, how they work is they create they basically create EVM, which is actually zk-fied EVM, because every opcode you execute on this EVM, every program that you execute on this EVM would also result not just in the correct state root, but also approve that this execution is correct.
You're going
So instead
from
of
zkRollups into zkEVMs now, right?
yeah, essentially, because like the core of a zk rollup is is a zk EVM, right?
Mm-hmm.
Because that's the main thing that they are trying to do. Uh, Other parts of the zk rollup is pretty much same as the optimistic rollup that we talked about earlier. That yeah, they will have the transactions and they will submit these raw transaction inputs to L1 for the sake of data availability. So withdrawal cannot be prevented. So I cannot keep withholding data if I'm a sequencer. But other than that, the important part of a Z rollup is that it uses a different kind of VM, which is which is which is trying to emulate EVM, but also producing validity proofs when it emulates it, so that we know that every instruction that is being executed in this VM is actually valid, and that's the really the magic that we need to avoid this challenge period that we described earlier. So if you're a roll-up sequencer and you are executing the transactions, but with the transactions you can also produce the validity proof, and you submit that validity proof along with the new state root to the L1, then nobody needs to wait 7 days or 14 days or however much time, and even the composability doesn't break. So yeah, you could just um, ideally you could just assume that like that if the validity proof is correct, then the execution happened on L2 and it is correct, and just move on. So that's how zkRollups can enable scalability on Ethereum.
Yeah, thanks to some wizardry, we're able to prove hopefully that all of these transactions, these state transition is correct. So essentially, on that piece, and maybe to drive it home, that there's different approaches, and the two main ones essentially being these optimistic, and then these like zk rollups. So in the optimistic, you're in both of them, you're sort of executing these transactions on like these rollups themselves, and then publishing the results, as well as the actual inputs to the transaction. You know, this state transition function essentially that you're applying on the rollups to the L1, as well as like the data, so that it can be verified. So in that case, it's a challenge period, typically that 7 to 14 day or so period, so that everyone can ensure that that's the correct. Then you have on the flip side of optimistic, you have these like zk rollups where you now also submit a proof, and the hope is that if you can verify this proof, you know that all of the transactions that have also been submitted are valid. And this does sound like some wizardry here at play. Uh, and you know, in some future state, it like opens up the doors. Maybe it feels like, yeah, fully magic. This thing that is, you're able to reduce so much computation, as like we're kind of working with like the succinctness benefit of proofs really as a whole, is like you brought up earlier, that point of reducing the amount of essentially like deduplicating compute, right? So if you want to just view it from a purely resource side of things, is you're hopefully using the resource once and then able to use a very small amount rather than replicating it and having to rerun all of these transactions themselves in order to verify it. Um, yeah, yeah, and then on the like I guess the and a brief piece here, yeah. I guess you had talked briefly on the sequencer and a little bit of like that flow. I didn't want to interrupt, but maybe just summarize some of those points that you made as you went through. I thought those were great. Um,
Yeah, that was a great summary. Um, yeah, I think uh, I think maybe we should like we could go into the ZK side of things, but like that's like a whole rabbit hole, right? Because every there are like bunch of roll up teams and they're pursuing different types of proofs. The Polygon team, their proofs are mostly Stark based, hash based proofs. I think Scroll is mostly kind of Plonkish type proofs. Um, yeah, I don't know like how other projects are doing, but like yeah, there's a whole separate discussion and a rabbit hole that we can go into about discussing different trade-offs on different proof systems. Uh, but like we'll reserve that for some other time. Maybe this time like we can go a little bit into the importance of data availability for rollups, because like as we mentioned earlier, that the rollups the sequencer especially needs to put all the transaction inputs on the L1 chain, because that's what that is really important for the data availability. Um, and like let's say like if I run the sequencer and tomorrow I decide to like shut down my business and just go away, somebody like if all the transaction data is available on L1, right?
so yeah,
Somebody could just jump in. Somebody could just jump in and um, like create like a whole L2 state from the scratch, because all the data
mm,
was available on L1. So yeah, I think the data availability, especially with respect to rollups, is like super important, because that's like what makes it secure.
mm,
um,
mm-hmm.
that's what because even with the zk magic, we still need the state to be for the execution to run. We need to make sure that the state is available. And and yeah, so that's, I think it's pretty important to maybe focus a little bit on da, and especially like da is like yeah, something recently which is a lot of new projects have come, a lot of new projects like Celestia, and now Ethereum is also pursuing a peer DAS for their data availability sampling. There's EigenDA, and I think there's probably a lot others. Like there's Avail, which is doing something similar, I believe. So yeah, I think maybe we could go a little bit into how and why and what of data availability, maybe.
Yeah, absolutely. That was a great introduction into DA, and yeah, maybe we can go through a little bit of the hopefully the why, what, how of it. So like wrapping it back into rollups as a whole, we've kind of touched on the fact that we're looking to scale, and by like scale, it means that we want more possible like applications, essentially more users to be able to use this technology, right? You have this base layer of Ethereum, and there are certain restrictions. It's highly secure, um, decentralized, and like then also distributed, right, all across the world. But there's certain things that it does well and certain things that it doesn't do well. So we introduced like rollups as being able to offer this opportunity to increase the scalability, essentially, like, you know, make experiences that feel a little bit less like blockchain specific, and get users directly away from the backend services, these like sort of cloud-esque, web servers that we're kind of having, and abstracted away because the user experience can be improved through, increased like transactions like per second, and this sort of uh, essentially getting a better user experience thanks to some of the benefits of like higher throughput and the benefits we get with rollups as a whole. And data availability comes into play as you're no longer executing on the actual layer one, right? So settled to Ethereum itself. There's two things that are essentially being published. Or I guess to the L1 itself is like the final sort of state, as well as the actual transactions, the inputs, right? So if you want to view all of these blockchains as a big transition state sort of machine, you got time at 0, time at 1, and you do a bunch of things, right? Maybe I send you all of the Dogecoin in the world in between time 0 and time 1. That's a state like transition, right? So you need to be able to ensure that all the transactions that have been executed are correct and valid. So you need to publish all that data. And right now it currently works. And I didn't mention then for zkRollups, you would also, I guess, be making available the validity proofs, right? So hopefully you don't have to run all the transactions yourself. But in short, essentially you need a way to be able to make sure that all the transactions are correct. So these rollups publish all the inputs so that anyone in the network is able to verify that the state of the network is then correct and that these transactions can be included. And currently it's using Ethereum. Was like the first sort of level, or rather, like, let's say you can generalize it to like an L1 itself, and it's using the L1 for data availability. So publishing the actual data in the form of call data, and then you brought up 4844, and so call data, right? So you're essentially paying gas, and those gas fees could be potentially high, and you're still just sending transactions, and it's required for every transaction to then be included, when you're publishing this data in the form of call data. And now, fortunately, we have 4844. So blobs, binary large objects. So now you can store even more transactions and hopefully reduce then the cost, that's incurred per transaction. And we're still working at kind of broadband or dial-up level speeds with this, as you can increase the amount of execution that you have, as far as like actually being able to do these state transitions on the rollup, but you're kind of getting bottlenecked now by the data availability layer that you're using. What I mean by that is that you have to publish this data, and you have to figure out, like, you have to ensure that it gets published. But if you're working with, right now, it's roughly like kilobytes of data that you can upload onto the Ethereum network itself. So then there's this need for sort of like, when people talk about modularity, it's kind of like breaking away different pieces, right? So you get like execution. There's also like data availability as like one piece of this, is that you can have these building blocks of roll up, essentially, or I guess like your complete service. So you would like something that's a little bit faster and maybe like specialized for data availability as a whole, and you need something that's like higher throughput. So we're kind of working in early stone age-ish, it feels, as far as if you're only using like working in sort of kilobytes. And now we're starting to have the opportunity to even have like megabytes of data, and that might not sound crazy in the grand
just
Web2
on the,
scheme of things.
that's a really interesting point that you mentioned about like the cost of it, because like if it's really expensive, you would only you don't only want to put like kilobytes of it and not megabytes of it, because how expensive it could get. And rollups also have to, like, in the end of the day, they have to pay their AWS bill, right, or whatever. So that's where the profit margin would come, right? If they're paying like too much for the data availability on L1, then like they're getting less for each transaction that happens on L2, and which kind of leads us into like an interesting point, right? Where like data availability on Ethereum is like expensive, because obviously it's more decentralized and more secure blockchain. So so people are willing to pay more just to have that extra security. But like recently we have seen in, like, for instance, Optimism has a Rollup SDK, so does Arbitrum, and so does other Rollup foundations, and they are creating this SDK for anyone to spin up their own Rollup pretty fast. And a lot of these SDKs are modular. They allow you to choose their own data availability layer. For instance, like if you think it's secure enough to post these transaction batches on Celestia, then you might as well do that, right? Because it might be 1/10 of the cost or even less or something. So yeah, yeah, maybe like maybe we can talk a little bit about alternatives to Ethereum DA, which may not be as decentralized and secure, but uh, but can be cheaper. So yeah, that could like as a rollup developer, you might want to use like some of those alternatives. Maybe like we can describe like Celestia or EigenDA or and why it could be um, more appealing for some people than using Ethereum L1 as the DA.
Sure. Yeah, absolutely. Now there's an opportunity for people to be able to spin up rollups. Like the barrier to entry with rollups has really reduced, as now there's even services that you can click a few buttons and you have a rollup with using like rollups as a service. You know, you got like the Conduit, the alt layer, Calderas of the world, essentially enabling people to be able to spin up rollups super easily, or just you know these rollup SDKs. Right? You got the OP stacks, you got the Arbitrum orbits, zk syncs of the world that also enable that. And now you have an option, um, like you brought up. DA is not only just like a bottleneck for maybe like transaction execution, it's like cost, right? It's just like cost that you're kind of competing if you're using the native DA layer. It's pretty costly, and that's like yeah, you're almost like broken down to like an operational cost, right? You have to like think about it's not just like doing the actual data like execution itself once, but now you have to like pay to like you kind of have to pay again to publish this data and make sure that it's valid, and that's becoming not the case with like these alt DA layers is there's like some big pieces essentially of it. Like one that I think the initial focus it kind of essentially has been around cost reduction. I want to pay less for doing the same thing. That sounds great, right? Is essentially like reducing the cost that you have to pay up front, and yeah, I guess then how this typically like works in practice is essentially you implement an like a alt DA layer, like an EigenDA, Celestia of the world, and you then would send those transactions, right? So those transactions that you computed, you'd send them essentially to like blobs, then to this alt DA layer. And because it's specialized for data availability, and you're not competing with all of the other transactions that are going on in an L1, you reduce the cost, right? So this can be like a very significant cost decrease, right? You could be paying, I don't know, you could be paying a fair bit on the L1s, right? As you're also up to sort of a dynamic fee pricing that might happen, right? You've seen congestion happen once or twice, whether there are massive gas spikes that then you have this also volatility, right? To maybe this like operational cost that you brought up before. So essentially implementing an LDA, what that means is that you're then like sending the data to this data availability layer. Then the participants of the data availability layer are making that data available so that you can retrieve it, verify it at any time. And since these are specialized, the cost is often cheaper. And then the other thing, and that was like, a big piece that people were initially looking at was like cost reduction. And then we're also um, seeing that there's a requirement for like high throughput and like scalability, right? You're looking at companies that are getting, you know, thousands, tens of thousands, now even mentions of hundreds of thousands of transactions per second. Your bottleneck kind of is onto even how much data you can potentially post to a data availability layer. So the specialization and how that sort of works um, is like it's really important that you have like a high throughput essentially on these data availability layers. So to touch on essentially the flow, if you have a transaction, you're instead of publishing it to the L1, you're now actually publishing it to one of these data availability layers. It's like one approach I can speak to. The EigenDA approach is then it's sort of chunked using some fun, I guess, like erasure coding and cryptography that I won't necessarily touch on now, but broken up essentially and spread up throughout the network. And the network operators are then making that data available. So right now you can get up to like 10 megabytes per second essentially of throughput onto these DA layers. But essentially you just have all your transactions, you're stored in this sort of like buffer, this blob, and it's dispersed amongst the network. And then over the next, sort of like 2 week period, often for, both these optimistic, but the topic of like zkRollups, like typical sort of period that you would need to be able to verify and ensure that the blocks that are included in L1 are valid and good. But that's sort of how it would work at like a high level is essentially now rather than posting to an L1 directly, you post to this data availability layer and it's dispersed amongst the operators of that data availability layer. And the intention is also that you don't have every operator of the network, like the same way that you brought up, you don't want to execute 6,000 transactions on every single node. The intention is that you store less than the amount of data essentially on you don't do like O of n times n. Essentially storage is like every single node shouldn't have to store all of the data in the network. And some of that magic with like data availability sampling, essentially being able to get a small subset of the data that you would like to ensure that you can, if you want to be able to verify, you get like a little sample, and it gives you very, very, very high guarantees or assurance that the rest of the data, the complete data that you would like, is available. So that is maybe a fun topic for another time, is maybe some of the cryptography and distributed systems work on that front. That's kind of how it works at a high level, and hopefully it opens the doors. It kind of reduces the bottleneck that we have right now on DA.
Right. Yeah, I kind of find the data availability sampling pretty interesting because of just this fact that you don't have to store all the data on every node, but you can like spread it out, and which means that like even if you have nodes on the network which do not have that much storage capacity as other nodes, they can still participate by storing only a small amount of data. And as long as the sampling works fine, we can still have assurances that the whole data is in the network and it could be retrieved. So that's really a good topic maybe to cover some other time.
More magic. Yeah. Yeah.
Great. Yeah, one thing I was that recently comes up is the end game of rollups, and and a lot of noise recently has been made around the zk, and a lot of discussions around like why even optimistic rollups might want to become or slightly move towards being a zk rollup, or at least rely on validity proofs more, just because it can give their users this sort of better UX by removing the challenge period from their system. And maybe like that is an interesting topic for the future, right? Where maybe with I think that there was some work with like Optimism is collaborating with Risk Zero or a project like that, where they're trying to make validity proofs of a fault proof, and instead of posting the fault proof on L1, like even on L2 you can create a fault proof and create a validity proof of the fault proof, and then post the validity proof on L1, which is like
Hmm.
an interesting things.
It's like a little wrapper.
Yeah,
It's
we'll
like a
see.
nesting doll
Yeah, right,
of proofs.
right, right. Yeah, that's interesting, right? We'll see like what happens with those approaches in the future. But like at this point, it does seem like a lot of optimistic rollups would probably move towards incorporating more techniques from the ZK world. So yeah, like if I were to predict, like I would probably imagine that the bridge between optimistic rollups and ZK rollups would probably um, there won't be much distinction later. Like a lot of optimistic rollups would probably incorporate a lot of things from zk rollups, and then like maybe in the future we'll just call them rollups, and we probably won't need this distinction.
Hmm.
Uh,
Yeah.
yeah,
You saying we don't need
like
another
like
term?
snarks. Like we used to have like this clear cut distinction between snarks and starks like until 2 years
Yeah.
ago, and now they are kind of melding into each other.
Yeah.
uh, yeah,
Yeah. I'm for it. The simplification is great. We don't, uh, and it's interesting to see that yeah, people talk about, ZK is the end game. Feels like we got a little bit of more infrastructure, uh, you know,
hmm,
I guess to get there is like being able to process all of these proofs essentially. But there's a lot of people working on these problems now, and it's particularly exciting to see how many projects. I mean, sent you the that landscape of
yeah,
like the ZK,
yeah,
and the fact that it's congested, right, is great to see. Is that there's so many
yeah.
people working on these problems, and yeah, all for improved user experience as well. So if ZK is able to do that, all for it as well. And guess we're just getting more and more magic essentially out there in the world, which also sounds great. Love Harry Potter,
Yeah.
so I'll take it.
Cool.
Yeah. I'm not sure. I think that we kind of covered a fair bit here from generally why do you even need like a roll up, right? We have an L1. What does that necessarily even mean? Some of the specialization that happens there, zkEVMs, and
Yeah.
then going into like data availability and what that means and what the alternatives are there. And yeah, maybe heading towards the end game. I guess we won't really be able to tell where we are in that story until we look back at one point, but it seems like we're at least walking down towards that path. So it's exciting to see.
Yeah.
Well, sweet. If I think we kind of covered a fair bit there. I think for this zkIDMAs that pretty much covers it, and we'll catch you, I guess, then on another one soon.
Yeah. Excited for the new one.
Yeah.
Cool.
All right. Well, I'm gonna stay on
So,
the call, but yeah, yeah. I was just gonna stop recording real quick, stop streaming.